AP and Honors Chemistry. This is your first lesson of the course, and the first unit is called the Foundations Unit. It builds up the basic understandings that you need to do higher levels of chemistry. And the first lesson, Lesson 1, is on the subject of math for chemistry. So first we're going to talk about fractions. You need to be fluent in fractions, particularly when you're dealing with units of measure, and you'll see that a little bit in just a moment. But we'll talk about fractions that you're familiar with numbers. So first we're going to talk about addition and subtraction. So you use the crossing arrows to create a common denominator. To add or subtract fractions, the number on the bottom, the numbers on the top are called the numerator, and the numbers on the bottom are called the denominator. You need a common or the same denominator. So the simple way to do that is to cross arrows. So you take the denominator of the 1/2 fraction and you multiply the top and bottom of the 2/3 fraction by that. Then you take the denominator of the 2/3 fraction and you multiply the top and bottom of the 1/2 fraction by that, and you have 4 little multiplications to do. So 2 times 2 is 4, 2 times 3 is 6, 2 times 3 is 6, and 1 times 3 is 3. So now you have the same number in the denominator, a 6. And so 4 plus 3 is 7, and the 6 does not change. You do not add the denominators, you only add the numerators together. Okay, subtraction is done the same way. We're going to take the 3 and bring it over, multiply top and bottom by 3. Take the 5, bring it over, multiply top and bottom by 5. That gives you 9 over 15 minus 5 over 15, and that's going to equal 4 over 15. Now, multiplication of fractions. To multiply fractions, you multiply the numerator, the top, and the denominator, the bottom, straight across. Some students get this confused with proportions and they think they cross multiply. You do not cross multiply. It's just straight across. So 2 times 4 is 8, 3 times 5 is 15, and that's how you simply multiply two fractions. Now, it's possible you'd like to simplify fractions before multiplying. Now, the only mathematical operator that you can cancel across is a multiplication sign. You cannot cancel across a plus sign, a minus sign, or a division sign. Okay, only across the times sign. So you can see here that you have 3/8 times 4/9. So the 3 and the 9, 3 goes into 3 one time, and 3 goes into 9 3 times. So you can cancel that and make that a 1 and a 3. 4 goes into 8, as you can see easily. So 4 goes into 4 one time, and it goes into 8 two times. Now you've reduced the fraction. Now you simply multiply across the top. 1 times 1 is 1. And so now it becomes 1/2 times 1/3. 1 times 1 is 1, and 2 times 3 is 6. And so that's how you would multiply fractions, by simplifying before you multiply. Convert to multiply fractions and integers. So convert the integer into a fraction by placing a 1 in the denominator. So here you have 2/3 times 4. You simply make 4 into a fraction by making it 4 over 1. It's the same value, it hasn't changed. So now there's nothing we can cancel here, so it's simply 2 times 4 is 8, 3 times 1 is 3, and that's how you would do that. Now that's called an improper fraction when the numerator is larger than the denominator. Oftentimes you want to leave fractions as improper fractions because if you need to do further math with that fraction, with 8/3, it has to be as an improper fraction, not as a mixed fraction. So let's see how you convert to a mixed fraction if you need to do that. So an improper fraction has a numerator larger than the denominator. So 5 over 3, let's take that as an example. So you divide 5 into 3. So 3 divided into 5 goes one time. 1 times 3 is 3. And then you subtract, so 5 minus 3 is 2. So what you then do is you write 1 and 2/3. So you write the number on the top, the whole number, the integer, 1, and then you place the remainder, which is 2, over the divisor, which is 3. Now, if you need to go in the other direction, 1 and 2/3 will go back. You multiply the denominator by the integer value, so 3 times 1. Then you add the number on top, the 2, and then you place it over the result over the denominator. So it's 3 times 1 plus 2, which equals 5 over 3. and that would be your final answer. Division of fractions and integers. So this is actually division of two fractions first. You flip the bottom and multiply. Most of you have done this before in math class. So 2 over 5 remains the same. Then you multiply by the reciprocal. Reciprocal is when you flip a fraction over. So the 4 over 7 becomes 7 over 4. You can see that there can be some cancellation there, although I didn't do it here. So 2 times 7 is 14, and 5 times 4 is 20. We could have canceled the 2 and 4 first. And you can reduce that fraction. If you don't do the cancellation, you can reduce the fraction. So 14 over 20 are both even numbers. So you can see that they can both be divided by 2. So 14 divided by 2 is 7, 20 divided by 2 is 10, and that would be your final reduced answer. You should always reduce fractions. Okay, for integers, you place a 1 underneath the integer to create a fraction, and then you flip the bottom and multiply. So here we go. We have 2/3 divided by the integer value 4. You turn 4 into 4 over 1, and then you flip and multiply. So 2/3 times 1/4 equals 2 times 1 is 2, and 3 times 4 is 12. Again, we didn't cancel the 2 and the 4 as we could have. You end up with 2/12 or 1/6. Here it's the same thing. This time the integer value is on the top, so you turn it into a fraction by making it 6 over 1 over the fraction 2/5. You flip the 2/5 to make it 5/2. That gives you 30 over 2, and you can reduce that down to 15. Units of measure are essential in chemistry and other sciences. Units of measure are the word or abbreviation that comes after a number to indicate what you're dealing with. So if I say to you, do you want 10? Obviously your question will be 10 what? 10 pizzas, 10 books, 10 what? What are we talking about? In this example, books and pizzas are the unit of measure. They indicate what the number is referring. Units of measure can be canceled in the same way as numbers or variables. So really we rarely deal with numeric fractions in chemistry where we leave them as in fractions. We usually convert them to decimal numbers. However, the units of measure are going to be treated like fractions. You'll see as we get into examples in this class, you'll see that. Okay, so we're going to cancel them the same way we just did with numbers or variables. So you treat numbers and units that are not in fraction form as though they are in the numerator. So if it's only on one level, it's in the numerator. So here we have 3 moles per liter. Now, you've not been introduced to either of these units of measure. You don't need to know what they are right now. We're just concerned with the math. So 3 moles per liter times 4 liters. So now you can change the 4 liter is in the numerator. Okay, it's only on one level, so you assume it's on the top. So now what we could do is 3 moles per liter means 3 moles for every 1 liter. So you can make that a fraction like that. 3 moles over 1 liter, and the 4 liters over 1. You just turn it into a fraction. Now the unit of measure liters can be canceled across the multiplication sign like that. And the only unit you have left is moles. So that's going to be in your final answer. And so 3 times 4 is 12, and moles is the unit in your final answer. Any units that have not been canceled out will have to go in your final answer. For integers, place a 1 under the integer to create a fraction, then flip the bottom and multiply. So here we have 12 moles over 2 moles per liter. So we're going to turn the 12 moles into 12 moles over 1, make it a fraction, and the 2 moles, just as the example above, is 2 moles for every 1 liter. Now we can flip the bottom and multiply. So you can see you have moles on the top and moles on the bottom. They're going to cancel out. The only unit remaining is liters. So it's going to be 12 times 1 divided by 2 is going to be 6 liters. How many centimeters in 4.5 meters? So to convert, you must know the relationship between centimeters, cm, and meters, m. So that relationship is there's 100 centimeters equals 1 meter. This is called an equivalency. The equivalency can be expressed as 2 different ratios, 1 meter for every 100 centimeters, or 100 centimeters for every 1 meter. In other words, both of those are true statements. There's 1 meter for every 100 centimeters. It's also true to say that there's 100 centimeters for every 1 meter. So those are called conversion factors. centimeters. So how many centimeters in 4.5 meters? Now what we're going to do here is called dimensional analysis. It's critical that you learn this really well, and we're going to spend a lot of time on it in the first month and a half of the class, but we're going to use it throughout the class. So the conversion factors we already learned is 1 meter for every 100 centimeters, or 100 centimeters for every 1 meter. So this is read, there is 1 meter for every 100 centimeters, or there are 100 centimeters for every 1 meter. These are both true statements, but we need to choose one of them to go into the equation. So in solving this problem, the first thing you ask is, what are you trying to find? What do you want at the end of this problem? And the answer is, you're trying to find centimeters. So you begin with what you're looking for, and that's some number of centimeters. In this problem, it's the number of centimeters. Okay, and then what does the problem give you to start with? So way over on the left, you identify what you are given, and you're given 4.5 meters, abbreviation M. So this is the value this value is in the numerator because it's on only one level. So the relationship between meters and centimeters is 100 centimeters equals 1 meter. This can be expressed as two conversion factors, the two that you see below that we just mentioned. So the question mark means which one do you choose? You choose one of them. Well, now that you know how to cancel units of measure, you want to choose the one that cancels out meters at the beginning and ends up with centimeters at the end. So that would be this one. So we're going to go ahead and place it there. And now we'll rewrite it over here. And the meters cancel out. Meters on top, meters on bottom. So now you have, the only thing you have left is centimeters, which is what you want for your final answer. So if those two units don't match up, the units that you're left with after the cancellation and the unit that you're looking for at the end of the problem, you did something wrong. But centimeters is the only unit we have left, and we have centimeters is what we're looking for. So now we're ready to do the math. So it's 4.5 times 100 divided by 1, and that equals 450 centimeters. Okay, here's some basic units of measure that we use in chemistry all the time. And you'll see these pretty much every day for the rest of this course. The basic unit of mass is a gram, okay? And in chemistry, we can use mass and weight interchangeably. In physics, there's a distinction that you have to make. But here, as long as we're staying on Earth and doing our chemistry on Earth, grams is the basic unit of mass. In physics, you usually talk more in terms of kilograms, but here we talk in terms of grams. Volume is liters. You've all, purchased a 1 liter bottle of soda. You know what that is. Distance is in meters. There are meter sticks in the room. Time is what you think it is, seconds, minutes, hours. It could also be calendar time, days, weeks, months, so forth, years. Temperature is either in Kelvin or centigrade. We don't use the Fahrenheit system in chemistry that's used here in the United States. And energy is something you're not used to talking about in everyday life as far as the units of measure, but it's called a joule. And that's a unit you'll see almost every day in class. Okay, so these are the prefixes. Those are words that come before that can be placed in front of a unit of measure to assign a number value. And there you go. You can kind of pause the video and review those, but here's the ones we use the most. Giga means 1 billion. That's 10 to the 9th power. Mega means 1 million. That's 10 to the 6th power. Kilo means 1,000. That's 10 to the 3rd power. Hecto, deca, and deci we almost never use. I will actually say we'll never use those. Then down below you see centi, which is 1/100th. That's 10 to the minus 2 power. Milli, which is 1/1000th. That's 10 to the minus 3 power. Micro is 1/1,000,000th. That's 10 to the minus 6. Nano is 1/1,000,000,000th. 10 to the minus 9th. And pico is 1 to the minus 12th, and that's 1/1,000,000,000,000th. A prefix such as a symbol such as mu, N for nano, or K for kilo in front of a unit of measure indicates a power of 10 to be multiplied by the number in front. Here are some common examples. So 6.7 micrograms is the way that would be read. Again, go back to that chart and you have a copy in your reference sheets that you can look at. The micro means 10 to the minus 6 grams. So you replace that symbol micro with 10 to the minus 6. So it's 6.7 times 10 to the negative 6th. Over on the right, you can see it if you wrote it out in full decimal notation. Generally, very large and very small numbers, we're going to use scientific notation, and we're going to get to that in just a moment. 430 nanometers, that's 1/1 that's 10 to the minus 9th, so it's 430 times 10 to the minus 9th. And 230 kilojoules, that's kJ, that's 230 times 10 to the 3rd. Scientific notation is a way to convert very large or very small numbers to a shortened length that's more manageable to work with and to write. So example, the speed of light is 300 million meters per second, but in scientific notation it's 3 times 10 to the 8th meters per second. We're going to come across a number called Planck's constant, which is 10 to the minus 34th. That means you'd have to write a whole lot of zeros to express that number in decimal notation. So the parts of a scientific notation number are the 3 out in front. The number out in front is called the coefficient. The 10 is called the base, and the base in scientific notation is always a 10. And then the exponent you're familiar with is the power that it's raised to. Converting from decimal to scientific notation. So move the decimal to form a number between 1 and 9.999. You can't say 1 and 10, but 1 and just up to 10, 1 and 9.999. Count the number of places the decimal was moved. If the original number was greater than 1, the exponent is positive. If the original number is a positive number between 0 and 1, the exponent is negative. Note, a negative exponent does not mean a negative number. It is a positive number between 0 and 1. So convert from decimal to scientific notation. So a comma in the United States is for readability only and can be removed. In some countries, the comma is treated like a decimal point, but not here. So place a decimal at the end of the number. So you don't see a decimal there, but there's an implied decimal after the last 0. So there it is. So now move the decimal to form a number between 1 and 9.999 and count the number of positions the decimal was moved. So think about that for a second. Where would you have to move that decimal to make it a number between 1 and 9.999? And the answer is you'd have to move it in between the 4 and the 6. So 4.67, even with zeros after it, is a number between 1 and 9.999. Okay. Now the decimal was moved 4 places and the original number is greater than 1, so the exponent is plus 4. So that's written as 4.67 times 10 to the 4th power. Do you need to include those zeros there? We'll talk about that in a later lesson. Maybe, maybe not. Convert from decimal to scientific notation. So take this number. So where do you have to move it to make a number between 1 and 9.999? The answer is right there between the 8 and the 2. So 8.2 is between those two numbers, 1 and 9.999. Okay, now you moved it 3 places, and the original number is less than 1. It's a positive number, but it's between 0 and 1. So the exponent is negative 3. So the answer is 8.2 times 10 to the negative 3rd. So note, a negative exponent does not mean a negative number. It is a positive number between 0 and 1. Okay, now we're going to go in the other direction. Convert from scientific notation to decimal. So write the coefficient by itself and move the decimal the number of places of the exponent to fill the blank spaces with zeros. So you write a 6.7. Now you move it to the right. How do you know you move it to the right? Well, because 10 to the 3rd equals 1,000. That's definitely a number greater than 1. So your answer is going to be a number greater than 1. If you had moved it to the left, it would have been a number less than 1. So you move it 3 places, and then you fill I call it the egg carton. You fill the egg carton with eggs. So the exponent is positive, so the number will be greater than 1. And there you put zeros in those 2 empty spaces, so now you have 66,700. You don't write the decimal necessarily after. Again, we'll talk about that at a later lesson. The decimal can be eliminated if there are no digits to the right of it. How about this one? Write the coefficient by itself. There's the 2.1. Now you see it's a negative 4. That means it's going to be a number less than 1. So to make 2.1 a number less than 1, you would have to move the decimal to the left. And you do it 4 places. So your answer is 0.00021. The exponent is negative, so the number is between 0 and 1. And there it is. A leading 0 should be placed to the left of the decimal. It's just a matter of convention, of style, that you should put a leading 0 in front of a decimal point like that. So now we're going to do multiplication with scientific notation. So 4.1 times 1.8. So what do? You multiply the coefficients and you add the exponents. So 4.1 times 1.8, and then 7 plus negative 2. And what you'll end up with is 7.4 times 10 to the 5th. So 4.1 times 1.8 is 7.4, and 7 plus negative 2 is positive 5. Now we're going to multiply a non-scientific notation number with one that is in scientific notation. So the rule is simply multiply the decimal number, the non-scientific notation number, with the coefficient of the scientific notation number, and adjust the exponent if necessary. So there we have 3.6 times 2.3. That's going to give us 8.3, and you don't need to do anything with the base and exponent. It stays as 10 to the minus 6. Now we're going to multiply the following. This is going to require a decimal adjustment. So multiply the coefficients and add the exponents. So there we have those two numbers. You multiply 5.2 times 2.3, and then you add 3 plus 2. And that gives you 11.6 times 10 to the 5th power. Now, the rules say that the coefficient needs to be a number between 1 and 9.999. This is not. 11 is greater than 9.999. So what do? You move the decimal one place to the left. So you move it over, and now it becomes 1.196. Now you can't just do that without changing the value of the number, so you have to do something to the exponent. And that's going to raise the exponent from 5 to 6. So let's figure that one out. When you go from 11.96 to 1.196, effectively you've divided the number by 10. 11.96 divided by 10 is 1.196. When you raise an exponent by one digit, when it's 10 raised to an exponent, and you raise that exponent by one digit, you've multiplied by 10. So those two numbers have exactly the same value. The only difference is the bottom one meets our rule of needing to be between 1 and 9.999. So the way to think of it is, if you make the coefficient smaller, you need to make the exponent bigger. You need to compensate for that. So move the decimal to the left on 11.96, making it 1.196. Then the exponent becomes bigger from 5 to 6. The coefficient has been made smaller by one place, and so the exponent must be made bigger by one place. The two numbers above have the same value. If you make the coefficient bigger, then the exponent must be smaller. If the coefficient is made smaller, then the exponent must be made bigger. Now we're going to divide. The rules for division are you divide the coefficients and you subtract the exponents, just the opposite of multiplication. So 5 divided by 2 is no decimal adjustment is needed, so 5.2 divided by 2.5 is 2.1, and 6 minus 2 is 4, so 2.1 times 10 to the 4th. Adding or subtracting scientific notation numbers requires a common base and exponent. We almost never do this, but you should know how to do it if it does come up. So here you have 5 times 10 to the 3rd plus 3.7 times 10 to the 4th. So the base is 10 in both cases, but the exponent is different. In order to add those two coefficients, you have to have the same base and same exponent. So a common base and exponent can be created by moving the decimal to the left on the 5, making it 0.5. Then the exponent increases from 3 to 4. So the number on the left, we're going to make the coefficient smaller from 5 to 0.5, so we're going to make the exponent bigger by 1. So now it becomes 0.5 times 10 to the 4th. So now in both numbers you have a base and exponent of 10 to the 4th. That means you can add the coefficients. So 0.5 times 0.5 plus 3.7 is 4.2, and then it is 10 to the 4th. All right, and that takes care of your first lesson. It's a pretty quick lesson. It's a lot of math. Much of it you've had before, some of it you haven't, so you just practice it, but you're going to get practice with this every day, almost every day in this class for the rest of this course. All right, we'll see you on the next lesson.